Hello friends, continue with the same paper. Now the next question, that is question number 5a. Obtain the line and the phase value of the current and the voltage relationship between them in a three-phase or polyphase star connection. First of all, just go through the important terms of that star connection, that is a line voltage, line current, phase voltage and phase current. Starting with the phase voltage. The voltage is across the two terminals of any one winding is known as a phase voltage. That all the terms line voltage, phase voltage, line current and phase current are differ according to the types of connection, whether it is a star connection or in a delta connection. The next one, that is a line voltage. The potential difference, that is V, between any two line is known as the line voltage. The line current. The current passing through any one line is known as the line current. The phase current. The current flowing through any one winding is known as the phase current. Now I am just go through one connection, that is a delta connection. That is three phase like R, Y or B, A, B, C, etc. You can give any name. These are the connecting lines. So these are three lines, line 1, line 2 and line 3. We can say that they are suppose A, B and C. So the voltage between these two lines, that is A and B, is known as VAB. So ultimately your VAB is a line voltage. The line voltage between B and C are known as VBC, such like that, and between A and C, that is VAC, and the current passing through any line is known as line current, that is IA, IB and IC, and the voltage between any one phase is known as the phase voltage, that is like VAN. If you are talking that N is a neutral, then same thing for the here VBN, and same thing for here, that is VCN, and the current passing through that phase is known as the phase current. So these are the four important terms if you are talking about any kind of connection, whether it is a star connection or whether it is a delta connection, because both the connection are useful in a polyphase circuit. So these are the four terms useful for particular connection. Now just go through our topic, that is for the star connection, the relationship between the line voltage and the phase voltage for the star connection. In a star connection, your line voltage, any given voltage is by default considered as a line voltage or the line value voltage. So here the relationship between the line voltage and the phase voltage are line voltage are √3 times greater than the phase voltage. So now line voltage is VL and phase voltage is VPH. So we get that VL equals to √3 times VPH, and but obvious it is a same thing, same happen for the VPH, that is VPH equals to 1 by √3 into VL, or VPH equals to VL by √3. So this is the relationship between the line voltage and the phase voltage. Remember one thing, both the values line voltage and the line current and the phase voltage and the phase current, these all are the opposite with each other in a star connection and in a delta connection. Here the line voltages are √3 times greater than phase voltage, where in delta connection the line current is √3 times the phase current. The next thing, the relationship between the line current and the phase current for star connection. Here your line current, whatever your line current passing through the circuit is equals to your phase current, in particular in a star connection. Remember again one thing, whenever we are talking about the relationship between the line voltage, current, phase voltage and current, then you have to consider the which type of connection you are preferred. You are preferring the star connection or in a delta connection, because all these relations are different in star connection and delta connection. Currently we are talking about the star connection, so here your line current is equals to your phase current, but this will not happen or this will not same in a delta connection. If you are talking about the delta connection, where your line current is √3 times greater than your phase current in delta connection. So again these are the opposite, IL equals to IPH or IPH equals to IL in star connection. Again the equation of the power for the star connection, P equals to, as we all know that power equals to voltage is product of the voltage and the current, but this is for the single phase circuit. But if you are talking about the three phase circuit, then you have to say that P equals to 3 into power consumed by each phase. So ultimately we get that P equals to 3 into VI equation. So here the again here we are talking about the star connection, so it becomes that P equals to 3 into VPH into IPH cos phi, because the each individual phase power is consumed, that's why we are taking the VPH and IPH. For the star connection we get that VPH equals to VL by √3 and IPH equals to IL. So substitute the value of that VPH and IPH into that equation of P. So we get that P equals to 3 into VL by √3 into IL cos phi. Now you can write that 3 equals to √3 into √3. So √3 cancel out. So we get that P equals to √3 VL IL cos phi. See here, it's like that, P equals to 3 into VL by √3 into IL into cos phi. 3 you can write like that, √3 into √3 VL by √3 into IL into cos phi. Now √3 are cancel out, so finally we get the value of power consumed by each phase is √3 into VL IL cos phi. This is the power consumed by each phase for a star connection. This one is same, this one is for star connection, and it is same power equation VL IL cos phi for also delta connection. So power consumed by each phase is in a star connection or in a delta connection, both are equal. Now in a delta connection, just we go through the quickly the relationship between the line voltage and the phase voltage for the delta connection. As I told you that it is inversely proportional to each other, delta and star connection. So where in a star connection the line current and line phase current are equal, so here line voltage and the phase voltage are equal. So you can write that the VL equals to VPH or VPH equals to VL. This is the relationship between voltages, line voltage and phase voltage. The line current and the phase current equation are also opposite, or they follow the equation for the line voltage and the phase voltage. So here what becomes the IL equals to, you can write that the √3 times IPH, or you can write like that IPH equals to IL by √3. So ultimately again we are getting the opposite value of line voltage, line current, phase voltage and phase current in star and delta connection. The equation for the power for delta connection is already we proved that equals to P equals to √3 into VL IL cos phi, because put the value of VPH or put the value of IPH into equation of √3 into VL IL cos phi, you can get the value of P equals to √3 VL IL cos phi. So here the power consumed by star connection or power consumed by delta connection, both are equal. Now the next question, that is a example based on the star and star delta transformation. The question 5b tell that the balanced three-phase load polyphase circuit, the impedance is 6 plus j8, which is connected in delta as well as star across the 250 voltage, that is the voltage V, applied voltage, and the frequency f equals to 50 Hz. The three-phase supply. So calculate for that particular circuit phase voltage and phase current, line voltage and line current, and the active power and the power factor. First of all, any given example, you have to just differentiate the data given to you. So here we just kept the data which is given for us, that is ZPH, that is impedance 6 plus j8 ohm per phase, that is a impedance per phase. Now whatever, as I already told you, that whatever the voltage given to you, that becomes your line voltage and the line value. So here we are getting that the value supplied, that is 250 voltage, so that one become our line voltage VL, that is 250 voltage, and frequency f equals to 50 Hz. So just find out the value of active power, then cos phi, that is power factor, then IL, then VL, IPH and VPH, according to the equation which we already proven in the relationship in a star and delta connection. Starting with the delta connection, first of all find out the phase voltage. As we prove that relationship between the phase voltage and phase current, phase voltage and the line voltage, both are value equal. So phase voltage in a delta connection is VPH equals to VL, and already the value of VL is given, that is 250 voltage. So we find that VPH equals to 250 voltage. Now impedance per phase, that is ZPH. The equation for ZPH equals to under root of R square plus XL square. Now what is your R? R is your real value and XL is your imaginary value. So using the equation 6 plus J8, using the equation of 6 plus j8, where 6 is your value of R, which is real, and j is your imaginary value, or you can say that it is XL. So put the value in the equation of Z square, R square plus XL square. You just prove that R 6 square, that is 36, 8 that is 64, it is again 36 plus 64, that is 100. So the square of the 100 is 10 ohm per phase. So this is our impedance that we find. Now the phase current for a delta connection, that is IPH. IPH is VPH by ZPH. I equals to V by R, and here for us the R resistance is for our impedance, that is ZPH. The VPH, as we already get the value of VPH, that is 250, and ZPH is 10. So by taking the ratio of 250 and the 10, we are getting the value of IPH, that is 25 ampere. Now line current, IL equals to root 3 times IPH. So we find the value of IPH. So 25 into root 3 times, and root 3, 1 by root 3 is a point near about the 0.707. So you put the value of that, you can get that IL equals to 43.30 ampere. So step by step you just find out the value of IL, IPH, then cos phi, then ZL. Now the turn towards the power factor, that is cos phi. The power factor equation for power factor cos phi is R by Z. We already get the value of R, which is real value, that is 6, and Z impedance for phase, that is 10 ohm per phase. So by taking the ratio of 6 by 10, we are getting the value of cos phi, that is 0.6. And remember that the value of power factor is leading or lagging. You have to just mention here, and here we can prove that the value of power factor is very below the value of 1 for the comparison of the 1. So it is a lagging 0.6 lagging. Either it can be lagging, either it can be leading, or they are if the value of cos phi equals to 0, then it means that it is origin from the 0 level. Now the next one is active power. There are some power like active power, reactive power, and the apparent power. Here we have to find out that the active power, the value of the active power is √3 times VL IL cos phi. If you are talking about the reactive power, then it is √3 VL IL sin phi. And you have to just find out the apparent power, then it is P equals to √3 VL IL. But here I have to find out that active power, that's why I have to use the equation √3 VL IL cos phi. Now substitute the value of all the equation VL IL cos phi into equation of active power. You are getting that VL √3 into VL is 250, IL equals to 43.30 ampere, and cos phi equals to 0.6 lagging. So we are getting that P equals to 11250 watt. Power is measured in a watt. This is our active power. Now all the stuff can be find out for the star connection. The phase voltage VPS is VL by √3 time in a star connection. VL equals to 250 voltage by √3. So ultimately you get that 144.337 volt per phase. Now impedance for phase ZPH equals to under root of R square plus XL square. Impedance for phase for star connection as well as for the delta connection, both are equal. So ZPH for the delta connection 10 ohm per phase, that is same as for the star connection 10 ohm per phase, by using the equation of under root of R square plus XL square. Now the phase current, that is IPH. Here your phase current is equals to your line current. So ultimately by using the equation of I equals to using the Ohm's law V by R, we can put the value of that. IPH equals to VPH by ZPH. VPH equals to 144.337 and ZPH equals to 10 ohm per phase. So IPH equals to 14.43. Remember one thing, whenever you have to just find out the phase current for delta connection or star connection, you have to just clarify about the VPH and ZPH. First of all, you have to just find out the value of VPH, then you have to just find out the value of ZPH. Now by taking the ratio of VPH and ZPH, you can just find out the value